All right, so today is kind of a one-off. We're going to be talking about tooling, generally tools that are used in coding that you've been exposed to. But ultimately, what I'm going to do is I'm going to focus mostly on debugging and debugging tools because those are the most useful, at least at this point in your CS careers. Um, I'm going to be demonstrating a couple of debuggers today, just making sure that everything's right. Okay, good. We remember that we are on YouTube and we are on Piazza, so if you have questions, please go ahead and post there. But anyway, tools to write code are often just as important, if not more important in a lot of cases, than actually writing code. For example, you've already been exposed, in fact, every week you're exposed to a source control system, control systems, right? The one that has basically won all contests is Git, which is a distributed version control system. Right? That basically you can check code in and you can commit it to a repository, and the entire history of that repository is preserved. So if you have a bug in a particular, commit, then you have a bug that you can trace that back to an actual commit where they introduced that bug. And that allows you to, well, first of all, blame somebody, blame the right person, but also then it allows you to fix it, right? It also allows you to work collaboratively rather than having, passing back and forth your files on a memory stick or something like that, or a shared device or something. You are actually committing it to a cloud-hosted repository, and then everybody can get access to it, and everybody can work independently and push commits to the head and work all by themselves, not without stepping on each other's toes. There are lots of features to Git that you've only touched the surface of. You can create feature branches. You can branch off and then use that branch for implementing some new feature while the main development continues. And then later on, merge those together only after the feature is complete. Right? There are lots of other features that you can use with Git. It's just a tool that you're exposed to now that hopefully you get into the habit of using on a daily basis. If you are collaborating with somebody, make sure that you're using Git, so that you're not passing files back and forth through email or a thumbnail device or something like that. You've also been exposed to build systems, right? Systems such as make or CMake, or in Java, there's Ant and Maven. Right? Again, you've just had exposure to it. You've never actually had to write your own make file or write your own Ant script or anything like that. But you can, and especially with Eclipse, there's an Ant script running in the background that you never see for how to build the actual default project. Building code can be just as complex as the code itself, because you might have code that is intended to run on 5 different systems, and you need to build this component, build that component for that system, build a different component for a different system, build a slightly different for depending on what operating system you're using a completely different compiler for a different operating system or something. And also, of course, you've got within that umbrella, this is called DevOps, right? Which is development operations. Right? You've got a whole other, basically this is a job unto itself. In fact, when I worked in industry, this is now 10 years ago, we only had about 100 developers, but we had 2 dedicated DevOps people. We didn't call them DevOps back then, but that's what they're called now. Their entire job was just making build scripts, deployment scripts, right? In making sure that dependency management was taken care of, dependency management, both internally and externally. If you've got a reliance on an external library, you have to bring that into the project. You have to make sure that you're bringing in the right version of that, right? And then there's a bug in that, and so you have to go and get an updated version, and then you have to test everything. Testing scripts, right? That you have to, before you deploy that, you have to make sure that all of the tests run and all the tests pass. So this entire discipline, I guess you could say, this entire job is something called continuous integration. And automating that process is an entire role unto itself. Right? You've also had exposure to testing, in particular unit testing. Right? There are a lot of other types of testing, regression testing, load testing, acceptance testing, when you're actually testing it with the user. Here's the interface we built for you. Go ahead and try to work on it, and let's see if you can actually get the job done now, right? But we've focused mostly on unit testing here. But we've also focused on it in a different kind of aspect. Ad hoc testing, where it's just a one-off, sanity check. Does my code compile, and does it give me at least one answer, right? Then we formalize that a little bit more, right? More formal, automated testing, where you, or informal, I should say, where you were writing your own code to test your own code. And then, of course, you've also had exposure to formal unit testing. In C, that was CMACA, and with Java, it was JUnit. Hopefully, we're not requiring you to write, going forward, we're not requiring you to write these formal tests over and over and over again, because a lot of times that's just as much work, if not more work, than actually writing the code. But again, this all falls under, TDD, which is test-driven development. On a development team, you could have an individual that is completely dedicated to simply just writing the tests for the code that other people write. Or you could have entire teams, QC teams, quality assurance teams, quality control teams, whose job it is to make sure that that they're testing the code so that they break it, right? They try to break it to make it, good, right? There are some other tools, right? You've seen static analysis tools. Now, with respect to static analysis, I've only shown you one tool, I believe, so far. You have GCC as a linter. GCC as a linter, right? If you use GCC WAL, basically it's looking at your code before it compiles statically, looking for potential problems. Lint, things that are not necessarily bugs, but things that are probably not what you want there, right? Brush that lint off your shirt so that it looks a little bit better, right? You can also use another GCC W extra. That sometimes turns on even more warnings. They're kind of kind of getting into esoteric warnings that you really have to dive deep into it. Some of them you have to dive deep into it, but a lot of oftentimes they're also red herrings. Instead of red flags, fix this. They're red herrings. No, that's fine. That's intentional. Nothing needs to be fixed there. Right? You also have another compiler plus linter. You have a compiler called Clang, right, or CLang. That's just a compiler, another compiler. In fact, I think on the CS50 IDE, that's the default compiler. But you can use, well, here, where's Clang? There we go. Analyze. So you can compile with Clang and then analyze your program. So foo.c. I think we can show this on the CSE server, but it's also available in the CS50 IDE here. Well, let's go ahead and just try it with the CS50 IDE. Clang, analyze my code here with demo.c. Okay, it didn't. And then what do you do? I think you have to do something else. Nope. I guess that's it. It produced, I think, demo.original. Nope. Okay. I guess it didn't find anything wrong with it. But anyway, there's definitely something wrong with it. It just didn't find it. Anyway, I'll take a look at that and see what I was thinking when I put that in, because I'm pretty sure that there should be something in there. There's also on CSE, not on CS50 IDE, but on CSE. A couple of years ago, I asked them to install Facebook's Infer tool. It's a free and open source tool put out by Facebook. And what you can do is you can capture an analysis. It does an analysis when GCC does its compiling. You can also use Clang with this, so you can use any compiler that you want. And the first command here is to capture all of the analysis and then to analyze it after it, looking for potential problems. Again, it's a static analysis tool. And it's only available on the CSE server. It's not on the CS50 IDE. But I can show it to you. Actually, before we do that, let's take a look at what I'm actually looking at. Emacs bounds. So I've got 2 buggy programs here that we're going to work with today. So let's walk through this very small program line by line. What I'm doing is I'm creating an array of 100 integers, and then I'm iterating over them, setting them equal to 1, 2, 3, 4, 5, 6. Right? Do you see a problem though? No? Okay, good. A what? It's a dynamic array, yes. Do you see any problem? Okay, good. We don't see a problem then. All right. What about the second one here? I'm creating a dynamic string of size 5, and I'm trying to copy chris to it and then printing it out. See a problem there? Okay, good. That one's a little bit more obvious. But let's go ahead and see if Facebook's infer can decide what's going on here. Infer, capture, GCC. Let's just do bounds. That's the one that we just looked at. Right? All right, so it captures all of these, I think expression trees and a bunch of other things. There's a lot of going on under the hood there. So infer, analyze. Right. So it's going to analyze my code here, and it's going to come up with several potential red flags with it. For example, there's a memory leak, right? That I allocated this memory and then I never freed it. That's okay. That's kind of more of a red herring there because it's just a small main program. Who cares, right? But it can detect potential memory leaks like this. Null dereference. What happens when malloc fails? It returns null. I never checked for that, so it is possible that I am dereferencing a null pointer here. Now, that's not going to happen because 100 times 400 bytes, malloc's not going to fail. But if malloc did fail, I'm not checking for it, and it's a potential issue. Again, potential issue here with the null dereference. Right? And then there's definitely one memory leak there. Unfortunately, it could not find that I was going past the bounds of a lot of stuff. Okay, fine. But that's another tool that you can use to come up with more potential problems. I've codified all these in a document available on GitHub. It's a troubleshooting guide, and there are some additional tools there that you can check out. Dynamic analysis tools are a different category of tools. They don't work on your code, they work on your compiled program. And we've already seen valgrind here, right? So you can run it with all these checks. Check all memory leaks, a full check on all memory leaks. Show all kinds of memory leaks when you run my program. And again, it operates after you have compiled your program. It's a dynamic analysis tool. It monitors your program as it's running for potential issues at runtime. And that's why we call it dynamic instead. So let me go ahead and recompile it here. Remember to use the G flag, because that preserves the line numbers and the function names and the variable names and all that stuff so that it can be analyzed dynamically. Bounds. There we go. By the way, if I run it, looks like it's fine, right? Hello, Chris. Hello. Right? But when I run it through valgrind, and I won't do all those flags there, I'll just go ahead and run it as it is. Right? There, it came up with at least 4 different errors. Right? While it was running, even though when I ran it, it looked like it ran just fine. What were those errors? Let's start at the top here. There's an invalid write of size 4 on line 10. Why? Well, there's 0 bytes after the block of 400 was allocated. Remember, it was an integer array of size 100, 4 bytes each. I allocated 400 bytes, and then I went beyond that bound. Now do you see the code? More bounds. Now do you see what's wrong with this code? I go from 0 up to and including 100, right? This is not an idiomatic for loop. What should it be? Strictly less than. Right? Valgrind was able to detect that. Let's continue. What else was there? There's an invalid write of size 2 on line 14. Right? What am I doing there? There's line 14, by the way. So a lot more head shakes when I asked, do you see a problem with this? A string of length 1, 2, 3, 4, 5, can you fit chris into it? Nope. What do you need? That null terminating character. and it was able to detect that. Right? And then there's an invalid read of size 1. Because I put in CHRIS and an null terminating character, I went and printed it out. Right? And that was an invalid read there. Don't ask me why it was 2 bytes when I actually wrote it. There's something else going on there. Right? Maybe it's using 2 bytes for its null terminating character or something. Right? But 4 different errors, and of course then the last error is, I believe, memory leak, the same one that Infer found. Right? You allocated a string and you allocated an integer array, but you never cleaned them up. That's okay in the main. Right? Okay, so that's Valgrind, and you've seen it. You can do bounds checks. Remember that you can compile, you have to compile with that G flag. You'll still get the same report if you don't. It's just that you'll get these mysterious memory addresses rather than actual line numbers. Right? And then it's way harder to find out what the hell went wrong. Not only that, but it gives you the entire stack trace here. For example, here, Malik, you did a size 5 string, and then on main you tried to print it out by calling printf. Printf under the hood called vfprintf, and then that called something else under the hood, and you don't have access to any of that code. It was never compiled with the G flag, so obviously it's not going to tell you what the line number it is. In fact, this is just a shared object file. It's just a bunch of machine code. Right? So, but you can pretty much assume that the standard libraries are not going to have bugs in them. Right? If they do, then that's a huge issue that's affecting way more people than just yourself. Something that we'll look at later, probably, is perf testing. Perf testing is just short for performance testing. And the tools that you can use to test your performance are called profilers. If your program is taking a long time, what you can do is you can run a profiler on it, and it'll say that 90% of your computation time is done in this one function. That allows you to focus on that one function to improve it, right? And if you can cut that in half, then the entire program runs 45% faster. Right? It allows you to look at only a particular part of your program to see what's taking the most time, what's taking the least time. You can even generate heat maps out of this stuff of where you're spending most of the time in a program. Again, we'll look at this later, but gprof is what you can use on the command line. Right? What I want to look at today are debuggers and debugging. Right? All right, so when you debug, what you need to do first is, well, what you want to do, I guess, is identify the bug. Right? Once you've identified the bug, then now you have to go back to the drawing board and come up with a fix. Right? You have to identify the input that causes the bug. Right? How do you get an input that causes a bug? What process do you come up with inputs and expected outputs, test it? Oh, that's not the expected output that I was hoping for. There's clearly a bug here. What is that process? Test. Oh, say what? It's testing, right? It is unit testing. You come up with here's your unit that you're trying to test. You come up with an input and an expected output through some other means, and then you test it. And if it comes up rosy, great, you're done. But if it doesn't, and there's a disagreement, then that's when you need to start bringing in the debugger. How do you know that there's a bug? You have to have at least one test case that fails, right? So that you can actually run the debugger on that particular test case. You identify the input that causes the bugs because you need to make the bug reproducible. There we go. Using printf statements to view values or variables is a poor man's debugger. And this might be what you've been doing up to this point. There's a bug. What happens on line 5? Oh, okay, I'll just print everything out on line 5. Okay, now I see the bug, fix it, delete that print statement. Now there's a new bug. Restore that print statement. Go back and forth in all your print statements. Not only that, but it is not at all reliable. Yeah?
So, by bug, you mean like when the output isn't naturally accepted?
Yeah, when there's a problem, an error with the program, a bug in the program. The term bug is actually old. The folklore is that I forget who it was. I think it was Grace Hopper is given credit, but there was an actual moth in a mechanical device, or a mechanical computer, that was impeding its operation, and so they pulled it out and taped it to their their report and said, "I found a bug," but I believe that technically the term was used prior to that. I don't know why where it came from. It's folklore, right? But yeah, it was that's the apocryphal story that's where the term computer bug came from. It was an actual moth in a not a supercomputer, but a vacuum tube computer or whatever, right? But yes, doing printf is a poor man's debugger, and it's not at all reliable. In a computer or in a program, printing stuff to the output is actually a very expensive operation. So it doesn't just print every single character as you print it. It saves it in a buffer. So you print one statement, two statements, three statements. Those actually don't necessarily make it to the screen right away. Instead, they're put into a buffer, and when the operating system deems it efficient to do so, then it will dump it to the screen and read from the buffer or dump the buffer. Right? What could happen is you could have these three statements in your buffer, your program fails, and then the buffer dies. It never got to the screen at all, meaning that you think that the bug was up here before these three statements that never got printed, when actually the bug is down here after the three statements got printed to the buffer but never made it to the screen. Printf is not at all reliable, and that's true of most programming languages. Right? So what you need to do is you need to use a proper debugger. Using a proper debugger is better. Right? For C, that's going to be GDB, and for Java, it will simply be the Eclipse debugger. Okay. What does a debugger do? It allows you to simulate the operation of a program. You can pause the execution. You can take a look around. What are the variable values right now? Once you've paused, you can slowly go through your program step by step. Because, of course, programs will immediately execute and be done, right? That's way too fast for a human to look and see what's going on. But you can step through the program line by line. When it calls a function, you can step into that function and then continue line by line, or you can step over into the next line or whatever. Right? You can set breakpoints. My code is 1,000 lines long, but the bug is down here at line 900 or something like that, right? I don't want to have to step all the way down. What I'll do is I'll set a breakpoint down there, run the program up to that point. That's where I want it to pause, and then take a look around. You can set conditional breakpoints. I only want to stop it if this variable value reaches a certain value, 100 or something. All right? I'm going to show you all of this today on both of these debuggers. But first of all, I want to show you just one step up a debugger. If you're really interested, it's a graphical debugger on the CS50 IDE here. Here's the program, gcc g demo.c. Right? You might have seen this word over here, this debugger. Right? There's a graphical debugger available in the CS50 IDE. What you have to do is you have to set a breakpoint first. And to do that, you just click to the left of any line number. And then after you've compiled your program using the G flag, you can use debug 50. That's their custom debugger in the IDE that they've come up with, and then a.out. That's the actual program that we're running. When you launch that, the debugger comes over here, and then you can see that now it's run. It's paused execution at my breakpoint here. I can step through this function line by line by line. Of course, I'm stuck in a loop here at this point. I don't want to go over that entire loop. I'm going to go ahead and set another breakpoint dynamically, and then continue the operation up to that point, skipping all 100 of those iterations. Right? I can take a look at the variable values over here. For example, n is 100. S is null right now because it's before I've called malloc. If I step to the next line here, you can see that S now has a value, right? It is, or that's not S. Yeah, that is S. That's its memory address. You can go ahead and expand it out, and you can see that there's nothing in it right now. Right? If I go one more, you can see that it is, changed. Right? Now, when I expand that out, you can see CH, come on. All right. It's kind of, I can't expand that out to look at the entire thing. That kind of sucks. That's why I don't really like this debugger. It's a very rudimentary debugger. It's only one step up from printf statements. Unfortunately, so deactivate all breakpoints, and we'll just go ahead and go all the way to the end. There, great. All right, that debugger was kind of stupid. Right? Let's take a look at a much better debugger. So I'm going to go ahead and quit out of that right now. GDB. So let's take a look at this program first before we compile it and see what it's going to do, what it should be doing. Right? So I've got a couple of functions here. I've got a function that generates a random array and fills it, creates a random array of a particular size and fills it with integers 0 through 9 randomly. I've got an average function that takes an array of integers and computes its average. I've got a print array function that takes an array and just prints it out to the standard output. Don't worry about that default value. You can see that the implementations are down here. And if you just look at it line by line, maybe you can come up with what the bugs are, right? But maybe not. Maybe it's not so obvious, okay? So let's come back up here. What happens is we read in a command line argument. We generate a random array, say 10 elements, and we compute the average. We print it out, and then we print out the average. Pretty straightforward. So gcc array.c, and I'm going to suppress all the warnings so that you don't get any spoilers, because some of these bugs can be caught by a simple linter tool like gcc. Right? All right, when I run it, of course, okay, you have to provide an n. How big of an array do you want? An array of size 10. Segmentation fault. Right? How do I know where it died? No idea. That's why I need to fire up a debugger, GDB a.out. Right? Now, this is an interactive program. I am at the command line not the command line right now, but I am at the GDB command line. It's waiting me to type commands. This is what's called a TUI, a text user interface. Right? It's not like a graphical user interface like over here when we've got a debugger in Eclipse. Instead, it's a TUI, text user interface. I have to type the commands to tell it what to do. I could, of course, say, run my program. Now, when I run my program, yeah, don't worry about that. I get this error message here. Error, you need to provide the command line arguments. Well, I'm not at the command line, so how do I provide command line arguments if I'm not at the command line? You can set args to be 10. If you've got multiple ones, then 10, 20, 30, whatever. Right? So I'm going to set my arguments to 10, right? And then I'll run it. And of course, we see that we get this segmentation fault here. Where did the segmentation fault happen? I don't know. What I'm going to do is I'm going to go ahead and go with layout next, first of all. Does that look like my code? No. If you want to, you can take a look at the machine code. This is, what is this, by the way? The memory addresses and this actual code over here, MOV, call, ADL, jump less than, probably MOV. These are all assembly language codes. Remember, way back in the first week, you take a high-level C program, you compile it to assembly, which gets assembled into machine code. This is the assembly. So layout next, all right, layout next, all right, or layout, yeah, I'll just jump to what I want to show you, source. Oh, what? There's no source available? Didn't I compile it with the G flag? Oh, I didn't. Right? There's no source available because I forgot to use the G flag. Now there should be source available. GDB a.out. Right. And then set my args to 10. Layout source. Right. And it'll take a while here to load up, but there we go. All right. There's my source code. Right. It even preserves all of the comments too, so that you can take a look at all of it. Right. So what I'm going to do is I'm going to go ahead and run my program now. Run. Ah, okay. Sometimes you have to refresh it. Right? I didn't have to refresh it here. But here's where the segmentation fault happened. Is that where the bug is, though? No. Probably not. Right? But I can take a look around and see what's going on. So say print n. Well, n is 10. N up here is the value that we got in this function. Print a. Right? Okay. That's just a memory address. So print Dereference of A. If I dereference A, which is an array, I should get the first element, right? But it tells me that you can't access that memory. So there's something wrong with this array. All right? So I know, now I have at least a hint as to what the bug is. There's something wrong with that array. So let's go ahead and start the program over again. But instead of stopping when the segmentation fault happens, I want to go back in time and find out when the array got screwed up, because it only segfaulted down here after a certain amount of code. So I'm going to go ahead and set a breakpoint. Break at the main. That's the very top of the program. Break main. And run from the beginning. Sometimes it gets screwed up like this. That's okay. You can always go refresh, and it'll redraw the screen. Okay? All right, so I'm now at the first line of code here. What I can do is I can start stepping through this line by line and taking a look slowly to see what's going on. I can go ahead and go next to go to the next line. Next, and next. In fact, that next is so common that you can just go n. N. Right? Now I've read in n as a command line argument. Let's make sure that that worked. Print n. Right? That's not the next, right? But that's, okay, 10. Right? That's reasonable. That's what I set my command line arguments to be. Great. Next. 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 Right? And then I segfault. So it must have happened. And by the way, you can use the up and down arrow keys to scroll through your code here. So it must have happened somewhere probably here. All right, so I've narrowed it down. Everything was fine up to this point. It screwed up in the print array function. So probably it's not printf. Must be something wrong with my random array. Okay? So I'm going to rerun the program, but I don't want to stop at main anymore. I want to stop at random array. So let's set a breakpoint at random array. Clear the original main breakpoint. You can go clear main. Right? And I've deleted that original breakpoint. And you can see, by the way, that over here on the left-hand side, just like in the CS50 IDE, I could click over here. It's text-based. You can't click over there, but you can see where the breakpoints have been set. There's my breakpoint. Now let's rerun the program from the top. Refresh. There we go. Okay, so now I'm in the random array function. Let's go ahead and print out n. 10. Okay, so we're going to create an array of size 10. See anything wrong with that line of code? Nope. It's kind of dark mode there, so there we go. I don't see anything wrong with that. Print A. Well, obviously, there's nothing in there, right? So, next, next, next. It's being filled up with random values here. I want to know what those random values are. Let's take a look at the entire array. If I print A, that's going to be the memory address of the array. If I print star A, that's going to be the first element. If I want, but I know that there are 10 elements in there. If I want to print out the entire array, I use the @ sign and then the size of the thing that I want to print out. There. The first one was set to 6. The rest of them are all zeros. So next, 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 next. Print A, 10. All right, so it's been now filled up with 6, 1, 3, and I can continue this. Looks all good to me, right? Print A at 10. There we go. You can print individuals, of course. A of 0 will give me 6. Print A sub 9 will give me 0, right? I don't see anything wrong with this loop, though. Right? Do you? So let's go ahead and skip that loop, and let's go ahead and break at line 50. Right? And I'm going to continue the operation of this program because I don't want to have to go through every single iteration of that loop. Continue all the way down to line 50. Okay. Do you see a problem now? What's the return type on this function? Int star. What am I returning? Nothing. Yeah, void. So when I go next and I get out of this function and I return back to the original function, let's print array. Right? You see that you can't access it out of memory because you never returned it. Right? Okay. Bug number 1 identified. Quit out of GDB and fix it. Donk, donk. What should I have done? A. By the way, that was what the warning I was suppressing. You reach an end of a non-void function without returning something. Don't ignore warnings. Right? They mean something. Recompile with the G flag. Try to run it again. Right? So, computing the average of 1, 1, 3, 8, 7, and 0. Does that look like the correct average? Nope. Yet another bug. GDB a.out. Set args to be, let's say 5. I want a smaller array. Right? Layout, source. Right? Once it loads. So where would you suspect that this bug is going to be? Where we compute the average. So let's go ahead and break at the average function. And we'll run up to that point. Refresh. Okay. Refresh. There we go. We've received an array and we've received n. Let's go ahead and take a look at those variables. Print n. There's only 5 elements in there. Print a at 5, because there are 5 elements in there. And we see that we've got 5, 8, 9, 5, and 6. What should the sum there be? 27, 33? Okay. So, print, well, actually, what I'm going to do is I'm going to set a watch variable. See that what we're doing is we're summing these up. So we're going to sum up 5, 8, 9, 5, and 6. So I should expect this to change from 5, then to 13, then to 22, etc. I don't want to have to step, and then print every single time. So I'm going to set a watch on sum, and anytime it changes, it'll report the old value and the new value, right, as I walk through. Next. Sum will now change, whatever it was before to whatever it is now, and already I see a problem. It went from negative 1, 3, 4, 2, 2, 5, 6, 4, and 8 to 5 more than that, right? We did add 5. Success. But what did we add it to? What is this? Garbage, right? It's dead beef, right? So what did I not do here? I did not initialize my variable. It's just a sum. Yet another one discovered. So Emacs, and you can use GDB on the CS50 IDE. It's just that I don't have any real estate up here to do so. You guys at home probably have these big giant screens and have a lot of real estate to work with. But I don't have that luxury right here. So let's go ahead and initialize our sum value to 0. Okay, excellent. GCC, a.out, 10. Right. Okay, it's looking a little bit better now. Right? If I run it, let's just do it with 5 numbers here. 5, 5. Should the average of a bunch of integer values be an integer? That seems highly unlikely. Right? That seems highly suspect. So once again, let's go ahead and recompile and fire up GDB. Set args, I'll only work with an array of size 5. Layout source. Right? And let's go ahead and go back into that average function. Break average. Run up to that point. Okay. Let's go ahead and set a watch variable to sum. And I'll go ahead and go through this. Actually, before I do that, let's make sure that the old value, the old value worked, right? The old value was 1, 3, some random dead beef value, and now our initialization here set it to 0. Let's print out the array to see what we're working with. So it should be 3, then 5, then 14, etc., etc., etc. Right? So next. 3 goes to 5, 5 goes to 14, and I don't remember what the values were. Print a at 10, or 5, sorry. All right, what should it be next? 17 and then 20. Okay, 17, 20, next. Uh-oh, what's going to happen? All right, it didn't change, but what happened here? Yet again, I'm going beyond. Now, that's not the same bug, but that is a different bug. But I noticed that because I was going line by line here. Okay. Now, print sum, print n. Oh, actually, This sucks because the random array is actually going to be correct now. It is an integer value in this particular case. I should have done something larger. But what's the issue here? You'd end up with, here, let's rerun it. Yes. All right, refresh. Print A at 5. All right, 4, 4, 4, that's 13. Okay, 13. This will definitely show what's wrong here. I'm going to break at 59 and continue. There we go. All right, print sum, print n. 13 divided by 5 should be 2.6. Next, next, print the average that you received. 2. 2.6, not 2. What happened? Integer truncation. All right, quit. Fix it. How? By doing a simple typecast. Okay, and then I think that was the last bug that I had, a.out 5. But you're only able to do this by first coming up with a large amount of test cases, automating those test cases so that you don't have to go through this ad hoc process every single time. What is 9 plus 3 plus 7 plus 8 plus 3? Pull out your calculator. Yep, it's correct. Right? That is not at all repeatable. Okay? You would test each one of those things as a unit so that you know that if there's a problem with one unit, one function, you can isolate that function and look at its operations when you run your debugger. Okay? That is only the surface of GDB. I'm going to go ahead and give you all the other, these are not all the other commands, but these will be in the notes. You start your program with GDB, you type run, you can break at the main, you can go layout next, or if you want to jump directly to the source, you can go layout src. Right? Instead, if you're not interested in the assembly code, that is. Next, or shorthand n. You can print a variable, you can print an array, if you know the length. You can set another breakpoint at line 25, or you can set a breakpoint at a particular function. Anytime it's called, it will stop and pause. You can refresh, you can watch a variable, you can continue, you can set arguments, and then you can also set conditional breakpoints. Only break at line 10 if the variable x has a value of 21. That allows you to do some really powerful stuff. Right? That, if you've got a loop that is 1,000 iterations, it saves you from having to go next, 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 next to get to that 500th iteration. Because only stop this execution when my index variable I is 500. Then that allows you to skip the first 500 iterations and then pause the execution. If you get caught in an infinite loop in GDB, you can halt the program just by using Control-C like you would a normal program. It'll stop wherever it is at that point, and then you can take a look around. Why am I getting this infinite loop here? Right? Okay? All right. Same thing in Java. Right? So I've got a buggy program here. The debugger is up here. This is not the same program because I can't manifest the same bugs. But this little bug up here allows you to run it and switch to a debug mode over here. Over here, you can take a look at variables, breakpoints, expressions. I set a breakpoint over here there in blue by double-clicking. Right? So, what's going on here? Do I have any breakpoints? I don't have any breakpoints. I don't know why. Oh, so what's happening? Why did it stop there? What happened? What value does b have? 0, so I'm dividing by 0 here. Right? If I continued the execution, resume up here, I'm going to get a arithmetic exception. Right? Divide by 0. So, all right, I don't want to do that. Let me go ahead and get rid of that. That was a bug. Right? Terrible code anyway. So let's go ahead and continue. You can go ahead and just hit the bug again to restart the program. Right? And it'll run up till the next exception here. Right? There's something going on there, so let's go ahead and stop the execution and set a breakpoint so that we stop before that error occurs. Debug. Right? There. Now we stopped one line before that happened. Right? And we can take a look around. A is 10. I'm about to do A divided by B, but it's 10 divided by, and then what is B? That has a value of 20. Okay. Next. Here's the next button up here. Go to the next line. Right? What happened though after that execution of that line? B is now null. And you see that it's highlighted here. It changed. Right? That's your watch variable in Eclipse. Right? Continue. Go one more, and you see that it resulted in a null pointer exception. Right? What you can do is you can make a conditional breakpoint. Let me go ahead and stop this execution. And something's going on this line, or not this line, but this line. Right, there we go. Let's go ahead and set a breakpoint there. I double-clicked that, by the way. Actually, no, let's do it a different way. So what I want to do is I want to create a breakpoint based on an exception. I'm over here on breakpoints. This J with the exclamation point is an error. What I'll say is if you ever see a null pointer exception, stop the execution before it's about to happen so I can take a look around. Run it. There. We ran up to this point and we can see all the variables here. B is in fact null. That is a conditional exception-based breakpoint. And you can do it for any type of exception. All you have to do is add one, and then you can do it for any exception, right? Or you can search for your particular type of exception and invalid application exception in the JavaX library, right? And set that so that if that exception occurs anywhere in the program, regardless of whether or not it's caught or thrown or whatever, it'll pause execution at that point and you can take a look around. Let me go ahead and get rid of it. You can delete it with the X button up there. Okay. So let's get rid of this because obviously it's wrong. Right. There we go. Terminate the program. All right, let's start again. Right. And now we get a division by 0 error. Well, I'm not dividing by 0 here. I must be dividing by 0 somewhere else. So once again, let's go ahead and set an arithmetic exception breakpoint. Arithmetic exception. And we'll run the program up to the point that we get an arithmetic exception, and I can look at the variables. I can look at C, A, and sum. C is 0, so that's probably not it. A is 10, so that's probably not it. Sum is 5050. What iteration did this happen on, by the way? 100. There's I. So what I want to do, great, I've narrowed it down to one line here. What I want to do is I want to stop the execution, and I want to simulate that program, but only up to iteration 99. I don't want to have to go next 99 times. So what I'll do is I'll pause execution on line 28, and go over here. I'll get rid of this arithmetic exception. This buggy right here, you can go ahead and edit it. You can go ahead and make it into a conditional breakpoint and pause if I is equal to 99. One iteration before the bug happens. Save that. And you do have to save, by the way. All right, save. You see it, that it's not saved up here. Save, and what, 99, there we go. There. All right, let's go ahead and debug it again. There. So I am one iteration before that's about to happen. I see that the sum is not 50-50. It is only 48-51. And then I can go ahead and start stepping through this. Step, step. And now I see that sum has changed. Is it? Has it not? Or it will in the next iteration. Yeah, it will in the next iteration. So there we go. Sum then becomes 50-50. And if I go one more, then that's where the arithmetic expression occurs. It allows me to skip those first 99 iterations though, right? Rather than having to go next. That is the debugger in Eclipse, the basics. Okay. Any questions so far? Has everybody used the debugger before already? No? Okay. It is an absolutely essential tool. By the way, this is a perspective up here, and you can change back to your Java perspective once you're debugging. All right, so with the remainder of our time, I'll let you guys decide how much of last year's midterm you want to do as a review, because your midterm is next Wednesday. Again, the format is 1 second past midnight on, 12:01 a.m. on the 20th, Wednesday the 20th. Canvas will open up a PDF like this, and maybe a bunch of other files, starter files possibly, and you'll download it, you'll start working. It won't take you 24 hours. I had an LA do it, and he said that he was able to do the honors version of it in 1 hour. So figure maybe 2 hours at most, which is what I designed it for. But you'll have a series of programs. You'll have some programs in C, some programs in Java. Okay. You'll have that entire 24 hours to do it. It is due at 1 second before midnight that same day. You can submit to the web grader as many times as you want. There will be scripts that grade it, etc. It's just like a hack. You'll be graded on style, documentation, design, and correctness, just like a hack. All right? So here's last year's midterm. These were freebie points, FizzBuzz. Right? I think you did this in your lab or some variation on it. Print the numbers 1 through 100. Unless it's divisible by 3, then print fizz. If it's divisible by 5, then print buzz. And then print FizzBuzz if it's divisible by both. Pretty straightforward. Body surface area, you read in a couple of values. I think the height and the weight of an individual in kilograms and centimeters, and then you can estimate their body surface area. So it's something medical. Don't ask me. I just look for these things and I pull them off. And there are 3 different formulas that you can use to estimate the body surface area of an individual. I think it's actually used in anesthesia. Don't ask me though. Anyway, because it's another estimate of volume of a person, right? Without having to submerge them into a tank to measure the displacement. It's a good estimate. But anyway, you report all 3 of these formulas along with an average of those formulas. You write it in C, you write it in Java. Right? We could do that. Or we could do array exercises. So you compute, given an array, 2 arrays actually, you compute their dot product. The dot product is simply just their components. So if you've got 5 elements, take the first 2, multiply them together, take the second 2, multiply them together, add those all up. Right? There's a bias dot product where you only do that if they're positive. There's a filter positive that given this array, give me a new array containing only the positive numbers from that array. Then you do them all again in Java. So, what do we want to do? Yeah?
So is on next Wednesday when the test is open, is the SRC open?
The SRC will be open. We'll hold office hours. But the level of questions that we would answer are probably going to be far lower than, say, that we would answer on a hack.
So usually on Wednesdays, the SRC won't be open.
Why not?
Oh, is it?
Yeah.
Is it? Oh,
It's open Monday through Friday.
oh,
The break is only Monday, Tuesday.
the break. Okay.
Your Thanksgiving break is Thursday, Friday, or 3 days.
Okay, because I was looking at the schedule for the SRC. There's like blocks on. So that
Oh.
for, like 155
No. There's only a block. I'll check it out, but I think that there's only a block on the lecture for 155E.
Yeah, but like on the Tuesday and Thursdays there are like blocks, and the Tuesday was like.
Yeah, but you could still go there. You could still that's because they're holding labs. You can always go to one of their labs or attend virtually. Yeah.
Okay.
Yeah. Question?
Will this be like the hack where we can visit the grader?
Yeah. I never assign something that I can't grade automatically. At least halfway. Oh yeah.
So for the web grader, will it show like expected output, or will it just run?
It'll be similar to what you did for Hack 7. It generates random test cases, and then it'll report That's not it. That's not it. So you will need to do your own testing. And I think we do give you at least a little bit of a starter file to encourage you. You should be testing at least once before you hand it in. Yeah.
Is he going to use JUnit?
No. We should, but we don't. We should use it as in our tester instead. Instead, I just whip up a few quick test cases. Because I'm always having to go back to JUnit. What the hell is the, what's the annotation again? And because I'm not using it on a daily basis. Do we want to see any of these? Yeah. The what?
Yeah, the second one, but I also just had a general question. Can you explain the difference again if I want to use the ampersand or the star in doing the preference?
Okay, sure. I shouldn't have closed CS50. So the star is the dereferencing pointer to regular variable. The ampersand is just the opposite. Regular variable into pointer. Maybe we could demonstrate that with this filter positive here. All right, so get rid of this. Touch array utils.c and array utils.c touch array utils.h. All right, so normally what you would do is you would add documentation to this and make sure that you put in an author documentation as well. I'm going to skip that. Instead, that will be our header file over here. We'll include the standard library because we will want to do some error checking. We'll include the array utils that we just wrote. Right? And now let's go ahead and implement this function. Right? So again, what the idea here is that you're given an array, ARR, of size n, and then you have to go through and pull out all the positives, creating a brand new array and returning that array, reporting back to me what the new size is. Right? Because if I gave you an array of 5 elements, -2, 5, 3, 4, 2, 1, the resulting array would be of size 4, right? Excluding that -2. So you have to tell me how big that resulting array is. I could probably figure it out on my own, but then I'm doing your work for you. You're the function in this scenario. Right? All right. What's the first step that we should take?
Make the array.
Oh.
Change stuff.
Okay, we could make the array as the result. Right?
Error handling.
Always, always, always error handling. What could go wrong here?
If the array is null.
If the array is null, or
Or the
n is negative, or new size is null, because that is a pointer. That is a pass by reference variable. Why is it a pass by reference variable? I have to give you both an array, and now I'm the function. I have to give you a new array, and I also have to tell you the size. Can I return 2 things? Nope, I have to return one of those things in a pass by reference variable, a bucket, right? So if this is the case, then I'll simply just return null. There's nothing else that you can return here. Right? Okay. Otherwise, I should create a result array. But do I know how big that array needs to be? I need to go through first and count up how many positives there actually are. So for int I equals 0, I is less than n, I plus plus, the idiomatic for loop, right? If array sub I is greater than 0, remember it's positives, it's not zeros. Positives, negatives, zeros, neither. Right? So if it's greater, strictly greater than 0, then I will need to increment a counter. Right? Num positives, plus plus. I need to, of course, declare it. Ah, good. Is that enough? You should initialize it to 0. Once I have however many positives there are, I can now call malloc. Right? Malloc, number of positives times size of int. There we go. And then eventually I'll want to return that result. Am I done though? Did I actually copy over all the positive values? Nope. So once again, let's go ahead and do that. The result sub I is equal to array sub I. Is that going to work? Again, test, test, test. Right? But this is simple enough we could probably see that this is it just a one-for-one copy? Nope. If it's greater than 0, I copy it. But what's going to happen to my indices? Should they always map? Should they always match, I should say? Let's take a look at this example. If I'm copying this over, I don't copy 2. I don't end up copying 2. But then I go on and I copy, what are the others? 5, 3, 2, and 1. Or negative 2, I don't copy negative 2. Right? In other words, should this gap be here? Nope. So I probably need another variable. Okay, int j, because that's the next one. Where should I start with j? 0. Always initialize your variables. Then results of j is equal to I. So I'm iterating over the original array, 0 through n minus 1, but I'm only iterating j on the result array on the left-hand side. Is that going to work, though?
Yeah.
I need to make changes to j++. Right? And then at the end, am I done? Did I communicate the new size to the calling function? Nope. So here's your question. New size is a pointer. Can I set that equal to the number of positives? Not the way it is. Right? In fact, it's telling me. It makes an int star to an int without a cast. Okay? So this thing on the left-hand side is a pointer. This thing on the right-hand side is a regular old integer. So how do I change the thing on the left-hand side from a pointer to a regular old variable? I dereference it. This is safe because I made the null pointer check up here. All right? Yeah.
So in what case again would you use the type that you know?
If you wanted to return like make your own error codes. We're not making error codes here, so I think even in the exam I said if this does should return an error code, we didn't require you to make your own enumerated type. You just return 1. Right? You just have to return something that's not 0. Right? Yeah.
So in the test, we have, just like the hacks, we have to check for errors, we have to also do documentation and then format it correctly.
Yep.
The code then.
All that stuff will be graded on in the exam. Yours is worth 100 points. So 50-50 on Java. It's gonna be kind of the same thing here. There will be a basic program and then a bunch of array utilities that you have to do. Yeah.
Is there any partial credit for say a program that doesn't mind
Partial credit on the style and documentation, sure. And just like Hack 7, we broke up several. We broke it up so that failing the error checking, you could still get points based on correctness with a different test case. We separated all of those out so that if one failed, the rest wouldn't fail to run, and we do that on the exam too. Yeah.
We have to check for all the errors that we learned about, even though if it's not a test on the web.
Generally you should, but yeah. Sometimes we're not that thorough in our code coverage either, so sometimes you'll get away with it. I think that there is a rubric item for that. Obvious errors, regardless of what the web grader says or something like that. That's under design or something. Yeah, you get away with it. Somebody did that with the Hack 7. An LA pointed out that this code is wrong, clearly wrong, but it passed all million test cases. And I go, okay, well, all right, to do, let's add yet another test case that will completely fail, that is guaranteed to fail for that, but we didn't ding him on it.
So,
Yeah.
for your error checking, you wouldn't return null, would you?
In this case, that's the only thing that you can return because it's returning a pointer. But in a different one where you're returning an error code, you'd return 0 for no error, return 1 for, or at non-zero, whatever you want. We don't care. The grade checker just looks to make sure that it's not 0.
So when it's an integer pointer, you return null
Yep.
on error codes.
Yeah, that's the only thing you can return. Right? If you return 1, that's a memory address that doesn't belong to us. Right? Yeah.
So if you want to turn a regular variable into a pointer, that's when we use the ampersand.
That's when you use an ampersand, exactly. So we're running out of time here, so I'll just open up. Here's what we used last time. That's a bias.product. So, but you see here, I need to know what the result is, and so I pass in a bucket to make a regular old integer into a pointer. We use the ampersand, just like scanf. Just remember scanf. Right. Okay.
But, so result is still, after that is done, result is still treated like a regular integer.
Oh yeah. We didn't change it. Just like typecasting,
Right.
double, it only treats it for the purposes of that expression. It doesn't actually change the variable. It's statically typed. You can't change the type of a variable once you've declared it. Right. A language like, say, PHP or Python or JavaScript, which are all dynamically typed, there's no intrinsic or fixed type of your variables. You assign it a string, it becomes a string. You reassign it to an integer, it becomes an integer, magically, and at a great cost because that's the cost of interpreted languages. Other questions? No? Okay. Well, good luck. Have a good break. If you do have any questions, of course, I'll be available throughout the break on Piazza if you've got questions. But otherwise, I highly recommend that you get Hacks 8 done before Wednesday. In fact, get them done by tomorrow so that you have a free and clear vacation. Right?